All right. This is a first draft where this is a first draft of a presentation on broadly why the standard deviation metric, the standard deviation statistic is defined the way it is. The thing that I want to do in this presentation is start from some very simple measurement problems that we can sort of understand with natural language that are intuitively make sense, and build up to why we use the specific standard deviation measurement. Along the way, we'll also talk about the mean. So this session is going to cover two things. It's going to cover means, and it's going to cover standard deviations. We'll also talk about variance, I guess, in the midst of that. So the first thing is we're going to suppose that we have some true distribution. This is a population. It's normally distributed, so most of the values are in the middle, and then there's tails that go out on either side. And so this could be something like height. Maybe if we suppose that this is the true value, that this is what it looks like if you measured the height of everyone in the United States. You get a value like this around, you get a distribution like this around a mean with some amount of spread. However, if this is sort of like the true value of a population, most of the time, however, we don't know the true value directly, right? If I want to know what the average height of everyone in the U.S. is, the first obvious thing to do is to just take literally everyone in the United States and measure all of their heights, and then add them all together and divide by the number of people in the United States. And this will give me an exact measurement of the mean height of people in the United States. However, this is very expensive, and most of the time we're not actually going to take the whole population and use every person in the United States as a data point. Instead, we want to take a sample, right? We're going to measure a smaller number of people and use that to extrapolate to the population as a whole. That said, sometimes it is possible to measure the whole population. So as an example, I've been measuring my typing speed lately and doing typing samples, and I just record every single typing sample. And so if I want to know the mean of all of the sentences that I've typed in typing practice, that's pretty easy. It's all there in the spreadsheet, and I can just take the mean of them. And so the first thing that I want to point at is a difference in terminology, and that is the difference between a parameter and a statistic. A parameter is some value of the true total distribution, and a statistic is a way of estimating that parameter. So in this case, if we have a population, the population mean, which is usually represented with the Greek letter mu. This mu is the true mean. It's the value that we get if we literally took everyone in the United States and we measured their height and then we averaged them all together. That would be the true mean. But we are going to, instead of taking the true mean, we're going to assume that we don't know the true population values. I'm going to put this population stuff sort of over here behind a veil of ignorance, different than the veil of ignorance in philosophy. We don't know the specific parameters of this population. I guess we're going to assume that we think that it's normal. A lot of this generalizes even if it isn't a normal distribution, but I don't want to think about which parts generalize and which parts don't. So all we know is it's a normal distribution. And the first thing that we want to do is we want to estimate the mean of the distribution. And this estimator is a statistic. In particular, it's this statistic is the, what color should we use for this? This statistic is the sample mean. And the obvious way to estimate the sample mean is to take a bunch of data points. 1, 2, 3, 4, 5 that are randomly drawn from, we take a bunch of data points that are randomly drawn from the distribution, and then we take the mean and we average those data points, right? So here, let's just say the average is at this point. And we'll call, so this is the sample mean, which is often represented as y hat, I believe. Although I think it's I've seen a couple of different things. I'm not super confident about how it's often abbreviated, but I think y hat is one of them. And this is pretty basic. Due to the central limit theorem, I think, from the central limit theorem, the more... No, I'm not going to say anything about the central limit theorem because I'm not sufficiently sure what it is or how it works. But intuitively, it makes sense that if you just take some random points from the population and you average them, the average of you're going to end up with your mean of the points that you're sampling is in expectation going to be the mean of the full distribution. And that in expectation is kind of important because it's pretty unlikely to be at exactly the mean, right? You'd expect it to be off by a little bit. Maybe I can say some concrete reason why, or maybe that would be obvious to my audience. But we expect it to be an unbiased estimator. We're not, and like we can expect that it's always going to be, two things. One, it's unbiased. So although we don't expect that our sample mean is going to be exactly equal to our population mean, we don't think that it's in expectation going to be either too small or too big. The expected value of the sample mean is equal to the population mean. Also, the more data points that we have in our sample, the closer the sample mean is going to be to the population mean in expectation. One reason why you can imagine that would be is if you have a data set of only one, your sample has only one data point, then you could have the mean of that sample is just going to be that data point itself, and that is if you only have one data point, it's still most likely going to be in this middle piece, but it's much more likely that you're going to get something on the tails than if you have two data points. If you have two data points, then one of them's here, one of them's here. The chances of getting one here and one here is much greater than the chances of getting one here and one here. And so if you have one, if you only have one data point, it's a very small sample size, the likelihood of your sample mean being off is much higher than if you have more data points. And in the limit, if you just took all of the data points, your sample was just the whole population, then of course your sample mean is going to be equal to your population mean because they are the same thing. So you can sort of see in between, there's like, if you take just a single sample, you're pretty uncertain about how close it is to the mean. And if you take if you take the whole population, an n of whatever the n of the population is, then your sample mean is exactly equal to the population mean, and so as you get close, as the n of your sample equals the number of items in the population, you should expect the sample mean to approach the population mean, and importantly, it's unbiased. Okay, so that's the mean. So that's one thing that we probably want to know about a distribution, right? If I hear there's 100 data points, and I'm only allowed to know one number about all of those data points, where the average is likely to be pretty helpful for me. But another thing that I'm likely to want to know is some intuitive notion of how spread out these points are. Right? We could imagine, we know this is a normal distribution, but we could imagine that it's looks something like this. Where it's very spread out, or we can imagine it looks something like this, where it's not spread out at all. And in actuality, it's exactly this amount of spread out. And we want to have some way of measuring that, right? That's another thing that I would care about. So what's a very intuitive way that I might go about giving you, what's an intuitive statistic that I might use to measure how spread out a distribution is? So one thing that occurs to me is I might measure the distance between each of these data points and the mean of the sample, right? So if I have, so I'm going to call the difference between the sample mean and, yeah, I'm going to talk about the sample mean for now. The difference between the sample mean and and a given data point is the deviation. So if we label these 1, 2, 3, 4, 5, the deviation of this data point here is equal to 3 minus 1, which is equal to 2. And the deviation of this data point is equal to 3 minus 2, which is equal to 1. And the deviation of this data point is 3 minus 3, which is equal to 0. I'm going to play a trick now and switch the order here. So the deviation of this data point is 4 minus 3, which is equal to 1. And so if I want to know how spread out the distribution is as a whole, one thing I could do is just take the average deviation for each point. Right? Each of these points is associated with a number which shows how far away it is from the middle of the distribution. Maybe I could just add those together and then divide by the number of elements in the distribution. So that would be a formula of, let's use a different color, do black. That would be a formula of sample mean minus x1. X1 is the first data point, plus sample mean minus x2, plus sample mean minus x3, and so on and so forth, divided by n. So this is the first intuitive thing that occurs to me if I'm trying to calculate the spread of the distribution. And the way and the thing that I'm going to do is sort of iteratively modify an intuitive notion until we get to standard deviation. So this one is what we're going to call average deviation. However, there are a couple of problems with using the average deviation, and the first problem is that I did this switcheroo here, where I changed the order of this equation so that each of the numbers would be positive. Now I can't. Now that's not a very good way to define a formula. Is just sort of eyeballing it and being like, well, if it's on this side, then we should put the mean first. And so we need some way to express. We need some way to make the all of the values here positive, so that we don't get them canceling each other out, right? If we allow this deviation to be 2, this deviation to be 1, this deviation to be 0, this deviation to be -1, and this deviation to be -2, then the overall average deviation is 0, because these two cancel out, these two cancel out, and this one is 0. So that's no good. So we need to have some way to make all of the terms positive. And the standard way that this is done is just to square each of these terms. You might ask why you don't take the absolute value of each of these terms. So the first thing that I want to say about that is I think that it would be totally valid to actually, first I'm just going to write this here. So if we square each of these terms, that gives us the average squared deviation. This gives us the average squared deviation. Yeah, so you might ask, why don't we take the absolute value instead? And so the first thing that I want to say is it is totally fine. Like it would be a reasonable measure of how spread out things were if we took the absolute value instead of instead of squaring each term. Like in another alternative universe, maybe like you could have an edifice of science and statistics that was based on taking the average absolute value deviation instead of the average squared deviation. The reason historically why we ended up with squaring instead of the absolute value is because it's very convenient to have differentiable functions. And the absolute value functions look like these compared to squared functions, which look like parabolas. And it's much more useful to have a parabola as opposed to a v, because you can take the minimum of a parabola. Whereas you can do calculus to find the minimum of a parabola, whereas the minimum of a v shape is not differentiable. The derivative is not defined. And so you can't use your calculus tool set with it, which is inconvenient. And so we ended up using average square deviation instead. Okay, but there is still a problem here. And the problem is that average square deviation is biased. Meaning that if you use this, if you take the average square deviation of a sample, you are systematically going to get a smaller average squared deviation than is the true average squared deviation of the population. I'm going to try and give an intuition for why this would be. So one reason is, suppose, basically it comes down to the fact that in this formula, we use, oops, want purple here, we use the sample mean instead of the true mean. If you use the true mean, then your average squared deviation statistic is unbiased. It gives you in expectation the average squared deviation of the whole population. The problem is we have this veil of ignorance. We don't know what the true mean is, and so we're going to use our sample mean instead. So, but we could if we break the veil of ignorance for a moment and we just suppose that the true mean is actually at 4. Yeah. Let me see if I can clarify. Why is it always an underestimate? Well, basically, the sample mean, the mean that is the mean of all of your data points, is always going to be close. All of the data points are going to be closer to the sample mean than they are to the true mean, because the sample mean is defined from those data points. And so that, right, so a thing that you can think about here is, yeah, the sample mean is defined from those data points. Excuse me. And so we should expect that the data points are going to cluster around the sample mean more than they're going to cluster around the population mean. And as a result of that, our deviations are a slight underestimate. Or I don't want to say slight, depends on the scaling factor. The deviations are always going to be underestimating. To give some comparison, suppose that our sample mean in this data set we have, or excuse me, this sample we have a data point at 1, a data point at 2, a data point at 3, a data point at 4, and a data point at 5, and therefore our sample mean is 3. But suppose that I knew magically that the true mean, the population mean, was actually 4. That's to say that some of these deviations are going to get bigger, and some of them are going to get smaller. Right? There's an error term, and the error term is in this case exactly 1. It's the difference between the sample mean and the population mean. We need to add or subtract this difference to each of the deviations, and we can tell that overall, when we compensate for this error, the deviations get bigger because, see if this tracks, because we know that most of the data points, or data point weight, because the sample mean divides the total deviation in half. That's what the sample mean is. That means that half of the deviation is on one side of the sample mean and half of the deviation is on the other side. Right? It doesn't mean that half the data points are on one side. It might be that all of the data points are on one side, and then there's another, except for one, which is on the other side of the mean, but it's so far out, it's such an outlier, that the deviation of that one point is equal to the deviation of all of the other points. But the sample mean is going to split the sort of total deviation of the sample in half. Which is to say, and we also know that all of the data points on this side of the sample mean, this side of the true mean, are going to get a little bit bigger, which means that more than half of the total deviation is going to get bigger, because this is half of the total deviation. Half of the total deviation is from these data points, and then there's this half, and this range, let's use a different color again, this range is half of the deviation plus a little bit extra. Which is to say that when we add back in the error term between the error of the difference between the sample mean and the true mean, more than half of the deviations, more than half of the overall deviation gets larger. So this statistic is unbiased, is biased, excuse me, not unbiased, biased, and therefore it's not a good way to measure the. We can't use it to measure the true population average squared deviation. So what do we do about that? Well, there's one simple trick, which is we change the denominator to n minus 1. And this, by the way, is the 3 population, excuse me, okay, never mind, not population, the other one, sample variance. This formula represents the sample variance. So you might be looking at this and wondering, well, okay, I get that the that we know that this sample, I get that average squared deviation is going to undershoot the true average the sample average squared deviation is going to undershoot the population average squared deviation, and so we need to make it a little bit bigger somehow in order to compensate. But how do we know that it's exactly that making it bigger by the amount of, by decreasing n in this way is the right amount? And I can say two things to that. So first, just empirically it works out. I'll link to some Khan Academy simulations in the description if this goes on YouTube, which I guess probably should. I'll link to them somewhere. And so one thing is you can just try it, and you'll see that n systematically undershoots, and n minus 2 systematically undershoots, but n minus 1 gets it just right. On average, it's an unbiased estimator. The expected value of the sample variance is equal to the population variance. Again, this doesn't mean that it gets exactly the right answer every time. It's still a statistic. It's still an estimator. But we have no particular reason to expect that it's going to be underestimating or overestimating. One way to sort of get the intuition for why this would be is that we know that the situation where this problem is worst is when we have a sample of of 1. So let's say we have let's say we have a sample of 1. I'll draw it down here. One data point. Let's say, like this, that data point is at 2, but the true, actually, okay, that was not a good way to draw things. Let's say that the data point is at 2, but the true mean is at 4. Well, if we're taking this formula, that means that the sample mean is, of course, going to also be 2. Sample mean And so we end up with the sample mean minus the data point minus x2, or excuse me, x1, which is equal to 2, equal to x1. Oh, these are bad colors. Squared over n, which is equal to two. All right, I'm not dealing with the colors anymore. 2 minus 2 squared over 1, which is equal to 0 over 1. And the difference is the true value in this case is equal to, actually, I guess this is misleading. Oh, right. It doesn't make any sense to think about this with a sample of 1 because the deviation from a sample of 1 is going to be equal to 0. But with a sample of 2, well, so I know that I should end up with n minus 1. All right, well, let me think about that for a second. Let's say 2 and 1. All right, well, I'm clearly missing something here. The punchline is that this formula does hold because the population, the difference between the population mean and the, excuse me, not the population mean, and well, it does work for, this formula does work. That's very not helpful. I'm gonna, my hope is that the next section of this, I'm gonna give a proof of why. But I'm definitely missing something. Okay, well, one thing we can say is that another thing to give the intuition is that the larger your sample size, the closer and closer the sample mean is going to come to the true mean, right? I think this is because of the central limit theorem, but I don't really understand the central limit theorem. In the limit, if your sample size was just equal to the population mean, you just took the whole population as your sample, then these would be identical. And so one thing that you can, so that is to say that you want your d-bias, the adjustment for the bias to get smaller as you add more samples, because as you add more data points to your sample, because this distance shrinks. And so having an n minus 1 here, means that as the n goes up, n minus 1 becomes smaller and smaller. Excuse me, n minus 1 becomes larger and larger. the 1 it becomes smaller and smaller in comparison to the end, becomes insignificant. And yes, as I said, so again, this is definitely not a proof. I'm going to present a proof of why this is true in the next section. Yeah. Yeah, but one thing to note is that if you are measuring the whole population, then you don't need to do the n minus 1. You can just take the average squared deviation. And this is why statistical programs like Excel or Google Sheets, very basic statistical programs, will have a function for the population standard deviation and the sample standard deviation, and the difference is whether or not it has an n minus 1 or just n here. Okay, but now we're at the variance, which is not quite standard deviation, and why is this? What's the last problem that we need to solve? Well, because we squared every term, that means that the units of this equation are going to be in squared units. So if we were measuring height in inches or in centimeters, now we have a we have a variance, sample variance, which is measured in inches squared. And this is not very helpful most of the time, and so we can just very naturally take the right here, just take the square root. And that gives us standard deviation. Excuse me. So, just to recap, we start with the average deviation. We average the difference between each data point and the mean, but that has a problem because some of those will be negative and we don't want them to cancel out. So we square everything to get the average squared deviation, but that has a problem, which is that because we're using the sample mean instead of the true mean, we're going to systematically underestimate the true variance of the population. And so we're going to adjust for that by changing the term that we divide by. And then we're going to take the square root of the whole thing so that we can, so that the units work out. So still the confusing part about this is, all right, so apparently empirically n minus 1 is the right number, but why exactly is that? And that's the thing that I'm going to cover next.